Hello, good evening to all of you. So, welcome to the first lecture of thermodynamics here. Okay, so before starting the lecture, just confirm me once that everything is okay now, screen and audio. My screen has been shared with you all. Okay, okay, okay. So let us start with the thermodynamics here. So first of all, let me tell you that the thermodynamics is going to be a very important subject for you for the thermal engineering part here. So in the thermal engineering, we have to cover up 4 or 5 subjects. The first one is the basic thermodynamics. This one here, which I am going to cover up in let us suppose in 7 days here. Just give me a second. I'm not able to write it here right now. Mhm. So first subject we have to see is the basic thermodynamics. Okay. After that, we will see the RAC portion. Then we will cover simple concept of IC engine. Then we will see the power plant and heat transfer. So these 5 subjects are interlinked with each other. Okay. Then we have to see the fluid mechanics along with hydraulic machines. And after that, we will see theory of machine. Okay, including vibration part here. So these are the 8 topics or 8 subjects which I'm going to cover here. So just tell me one thing. See, in this 2 month course, I am going to cover the numerical questions only. Okay, on the practice questions only. So do you want me to share the theoretical notes with you? Yes or no? If you want a theoretical notes, I will share it with you later on with this PDF. Otherwise, I won't be sharing the notes here. Okay. Okay, that is okay. So I will share the theoretical notes with you. Okay. So just go through the theory notes and then just go through the questions here. Okay. So this is the first class. So I'm going to cover up the basics only. So let us start with the thermodynamics part here. So just see here in this case, we are going to cover up the basic thermodynamics only. Okay. The applied thermodynamics you are going to see in these 3 subjects. So these are the part of the applied thermodynamics here. Okay, now what is the meaning of thermodynamics here? Thermodynamics is basically a subject, or I can say it is a branch of science which deals with the energy interaction here. Okay, it deals with energy interaction which is taking place between the system and surrounding. Now the question arises that how do we define our system? So a system simply means anything which is under our focus. Okay, now in thermodynamics, we define the different types of system here. We have an open system, closed system, as well as the isolated system here. So specifically in the basic thermodynamics, we deals with the closed systems only. Whereas if you just see in the case of applied thermodynamics, RAC, IC, engine, power plant, we are dealing with the open system here. Okay, so the complete analysis of the open system is going to be there in these 3 subjects, whereas the detailed analysis of the closed system is going to be there in the basic thermodynamics here. Okay, in the chapter in the subject number 1. Now let us start with the first question here. Now just see in this first question what is given to us. A closed system is one in which the mass does not cross boundary of the system, though energy may do so. Now just understand here the type of system which we cover up in the thermodynamics here. Okay. So like I have told you that thermodynamics deals with the energy interaction, and here we have different type of system. The first one is the closed system, then we have a open system, and then we have a isolated system here. Okay, in all the system the main thing is the energy interaction. Now the energy interaction can take place in the 3 different way. Either the work interaction can take place. Okay, either the heat interaction can take place, or either the mass interaction can take place. So due to these 3 interaction, the properties of the system may get changed, or we can say the energy of the system keeps on changing here. Okay. So now in this case, the number 1 and 2 point, the work interaction and the heat interaction comes under the category of energy interaction only, even though the third number point is also representing a energy interaction, but it is in the visible form. Okay. So we say it like a mass interaction here. So whenever you are classifying the system, In that case, you have to see that whether the energy interaction is taking place or a mass interaction can energy mass interaction is taking place here. Okay. For example, in the case of open system, the mass as well as the energy, both interaction can take place here. Whereas if we just see the closed system, the mass interaction does not take place. Mass interaction remain constant. Mass of the system remain constant, whereas the energy interaction can take place here. Okay. In the case of isolated system, the mass interaction and the energy interaction, neither of these is taking place here. And the one thing is you have to understand that when we talk about the energy interaction, these are always studied on the boundary here. Okay, so it is the energy in transit form. You always have to remember that whenever we are dealing with the energy are classified by two ways here. The first one is the energy in transit, and the second thing is the energy stored. Okay. Now, when we talk about the energy interaction, we are considering the energy in transit. That means the energy which is crossing the boundary of the system. Now, the energy crossing the boundary of the system maybe take place through the heat and maybe take place through the work here. Okay. So in this case, you can see uh, the mass does not cross the boundary of the system, though even though the energy may do so here. Okay. So that's a very simple case. And the next thing is, so here we have seen the type of systems here. Okay. Now coming back to the properties here. Actually, what happens here, whenever the energy interaction is taking place, either the work interaction, mass interaction, or the heat interaction, always the properties of the system get changed. Now, what is the meaning of property of the system here? Properties are basically representing the characteristics of the system here. Okay, for example, if I'm talking about the pressure, volume, temperature, all of these are the characteristics of the system which can be considered as the properties here. Okay, and there are different types of property: intensive, extensive, extrinsic, extrinsic. We will cover that part in the next in the coming up questions here. Now, the next part is according to the kinetic theory of gases, absolute zero temperature is obtained when. Okay, now just see. First of all, specifically in the case of basic thermodynamics, thermodynamics is studied in two different ways here. There are two different approaches to study the thermodynamics. The first one is the microscopic approach here. The second one is the macroscopic approach here. Now, coming under the microscopic approach, in the microscopic approach, we are dealing with the atomic or molecular level here. We are concerned with the changes which are taking place at the atomic or molecular level. But if you just see the macroscopic level, here we don't consider the atomic or molecular variation here. Here we are considering the average properties of all the atoms and molecules. Okay, so the approach which we used in our thermodynamics is the macroscopic approach, and this thermodynamics is also known as the classical thermodynamics here. Okay, so if somebody asks you that which thermodynamics you are covering here, you are covering up the classical thermodynamics. And whenever you are dealing with the microscopic, atomic or molecular level here, then you are studying the statistical thermodynamics here. From the word itself, you can see you are dealing with the statics. Statics simply means you are dealing with the individual data here. That means you are concerned with the individual data of atoms or molecules. Understood? Now, in this case, basically the kinetic theory of gas is a concept which comes under the microscopic or a statistical thermodynamics here. Now, according to the kinetic theory of gases, as you are increasing the temperature, first of all, the velocity is directly proportional to the under root of temperature here. So, as you are increasing the temperature, the corresponding velocity will be increasing, or I can say the kinetic energy of the fluid is going to be increased here. Okay, that is the statement of the kinetic theory of gases. So in this case, we define absolute zero temperature. Just see absolute zero temperature. First of all, what is the meaning of temperature? Temperature is defined as the parameter which basically tells you about the degree of hotness or coldness of the body here. Okay, as compared to some other body. Degree of hotness or coldness. Now, in order to define the temperature, we have different scales. Like we have a Fahrenheit scale, we have a Kelvin scale, we have a Celsius scale. So there are different scales here. Then we have a Rankine scale. Now, if you just see in the modern thermodynamics, the Kelvin scale and the Rankine scale are the very, very important scale here. And out of this, Kelvin scale is the most important scale here. Okay. So Kelvin scale is a scale in which there is no negative values are there. Okay. The absolute zero temperature is represented by 0 Kelvin. And at 0 Kelvin, there won't be any, I can say the kinetic energy of the theory, there won't be any molecular momentum or a molecular randomness present inside the system here. Okay, just remember that part. That is very, very important thing. So here you can see if the kinetic energy, if the temperature is 0 Kelvin, at that point of time, what is going to happen here? The molecular momentum will going to be zero there. Okay, the pressure will diminish. There won't be any pressure, and the corresponding kinetic theory of the kinetic energy of the gas will become zero there. Okay, so option number C will be the correct answer there. Any doubt? And how we have classified the different scales here. Okay, what are the different types of thermometer here? We are going to see it later on. Now coming back to the next part, the following are the example of some intensive and extensive properties: pressure, temperature, volume, velocity, and so on. Okay, now which is the correct one here? Now, first of all, what is the meaning of properties here? See, properties are basically the characteristics of the system. That's what I have told you. It is representing the characteristics of the systems here. So if the system is having a hot state, then how can we characterize that? We can characterize that with the help of temperature. If the temperature is 100 degrees Celsius, we can say that the system is at a very hot state. Okay, the hot state is nothing but is representing the characteristics here. In the same way, pressure, volume, temperature, all of these are nothing but these are the characteristics of the system. Now, if we classify the property, there are different ways. Here we have intensive property, which is also which can also be considered as an intrinsic properties here. Then we have an extensive property, which can be considered as an extrinsic properties also. Okay, intensive properties are those properties which are independent of the mass here. Okay, and the extensive properties are those properties which are dependent on the mass. Now, if you just see, the intensive is a word which we normally study in the thermodynamics. Intrinsic is a word which is normally studied in the material science. Okay, in your subjects. Extensive again is again a word which is studied in the thermodynamics. Extrinsic is a word which is studied in the material science. Okay, even though from the definition point of view, intensive and intrinsic both are having the same meaning. Both are having the same meaning. Extensive and extrinsic are both are having the same meaning, but there is a slight difference between these two. Now, what is the difference here? So now just understand. If we talk about the intrinsic property, these are those properties which are inherent to the system here. Inherent to the system. Now, what is the meaning of that? Example of intrinsic properties are the thermal conductivity, let us suppose, dynamic viscosity, let us suppose, pressure, temperature. All of these are the properties which does not depend upon the mass here. Okay. If you are changing the mass of the system, the corresponding properties are not going to be changed. Okay, so that means these are the properties here. Now, what is the meaning of intensive property? These four property can also be considered as an intensive property. Okay, now just see the difference here. Intensive properties are simply those properties which does not depend upon the mass. Intrinsic properties are those properties which are inherent to the system and does not depend upon the mass here. For example, the color of any substance or any liquid, it is basically an intensive one. Color is an intensive property here. Okay, it is not a intrinsic here. It is not a intrinsic. It is not a intrinsic, but it is an intensive property. Why I am saying that? Because if you have a color, if you just see, let us suppose if you have 2 liter of liquid, 2 kg of liquid is there. Okay, and it is having a red color. Now, if I just simply uh, take some water out of this container, okay, let us suppose you have taken 1 kg of water out of this container. Now, how much mass is left? 1 kg mass is left. Now, does the color changes? No, the color is going to be remain same. Okay, that means it is not depending upon the mass of the system. It is an intensive property. Now here what can I do? I can simply change the color of the system even though by changing the chemical compositions here. Even though by adding some impurities or by some means here, we can change the color of the system. Even though the color is not depending upon the mass, but it is not inherent to the system here. That is why we can say it is not an intrinsic properties here. Okay, so I can change the color by adding some impurities here, but the corresponding properties like thermal conductivity, viscosity, pressure, temperature, electrical conductivity, all of these things cannot be changed here. These are the inherent to the system here. Understood? In the same way, if we talk about extensive is a one which is dependent upon the mass here. Okay, extrinsic is a one which is basically defined, or I can say it is dependent on the system here. Okay, this is a little bit slight differences here. Now if we talk about the examples, pressure comes under the intensive here. Pressure comes under the intensive. Temperature comes under the intensive. Volume comes under the extensive. Velocity intensive. Electric charge intensive. Magnetization intensive. Okay, viscosity intensive. Potential energy extensive here. So here you can see 1 to 1247. 1247, pressure, temperature, velocity, and viscosity. These are the intensive properties here. Okay. If we talk about the volume, electric charge, magnetization, as well as the potential energy, these can be considered as a extensive one. Okay. Now just see. I have told you the electric charge and the magnetization as an intensive one because I haven't considered the mass here. But if when we are defining the total electric charge and the total magnetization of the system, it is depending upon the overall size of the system also. Okay, that is why it is considered here as an extensive one. Understood? So here option number C will be the correct answer. Is it clear to all of you? If you have any doubt, please let me know. So that's a very simple case. You have to be very careful about the differences between the intensive and intrinsic, even though it is not so much important, but you should be aware of that. Next, the definition of 1 Kelvin as per internationally accepted temperature scale. Okay, now just see the history of temperature scale, how we have defined the temperature scales here. Actually, what happens before 1954, before 1954, in order to measure the temperature, what is the meaning of temperature? Temperature is a parameter which is used to define the temperature, which is used to define or compare the hotness and coldness of the body here. Okay, this is the definition of the temperature. Now, over the period of time, there is a very large amount of improvement taking place in this accepted temperature scales here. Before 1954, the thermodynamics which we cover, which we study, is a simple one. Okay, that is a simple thermodynamics. After 1954, we have moved toward the modern thermodynamics. The thermodynamics which we cover today is a modern thermodynamics here. Okay, so before 1954, in order to define the temperature, we use a temperature scales, and the temperature scales are properly calibrated. So there we have to use the multiple points to calibrate the system or to calibrate the temperature scale. For example, there we define the oxygen point. There we define the gold point. There we define the sulfur point. Okay. Now, what is the meaning of oxygen point? Oxygen point simply represents you the boiling temperature of the oxygen. It is representing the boiling temperature of the oxygen here. What is the meaning of gold point? It is representing the freezing point of the gold here. What is the sulfur point? It is the boiling temperature of the sulfur here. So basically what we do here, we define any two temperature. We just take any two reference point to define the temperature scales. Basically it is used for calibrate the new temperature scale, or if you are creating your own new thermometer. Okay. Now, what is the value of oxygen point? Oxygen point is having a value of it is around minus 188 degrees Celsius something. Okay. Gold point is having a value of around 1063 degrees Celsius here. Boiling point of the sulfur is around 44.2 degrees Celsius. You can take any 2 point as a reference to define a new temperature scale. Generally, oxygen point and the gold point is generally used to define to calibrate the new thermometers here. Okay. In this case, this is how we define the temperature scale before 1954. Okay. So if you just see, uh, in the temperature range of minus 188 degrees Celsius up to 0 degrees Celsius, which thermometer we normally use here? We use a platinum resistance based thermometer here. Platinum resistance based thermometer. Okay. Now, why we have taken a reference as minus 180 degrees Celsius? Because it is an oxygen point here. Then we take a reference from 0 degrees Celsius to I can say 10. It is around 0 degrees Celsius to it is around I'm not remembering the exact value here. It is around 600 or 700 degrees Celsius, I think. Okay, from 0 degrees Celsius, yeah, from 0 degrees Celsius to 650 degrees Celsius, the thermometer which we use is again a platinum resistance based thermometer. Then from 650 degrees Celsius to up to freezing point of the gold, that is 1063 degrees Celsius, the thermometer which we use is the thermocouple. Okay, so these are the thermometers which we use for the different temperature range here. So in the case of the platinum resistance thermometer operating between the 0 and 650 degrees Celsius, there we assume that resistance is varying with the temperature as in this way. Okay, between the temperature limit of minus 180 to 0 degrees Celsius, the resistance is varying with the temperature in this way here. Okay, so there are different cases how we are assuming the variation of temperatures here with the resistance. And in the thermocouple, we simply calculate the value of the EMF, and there we define calculate the value of the temperature here. Now, after 1954, what we have done, we have defined a universal temperature scale. We have defined a standard temperature scale. Why there is a need of universal and the standard and the Newton temperature scales here? Because these thermometers, platinum, thermocouple, it basically depends upon the material of the substances here. Okay. Exceptional is the ideal gas thermometer. So there, after 1954 in the modern thermodynamics, we need a temperature scale which does not depend upon the material of the construction. Okay, it should be independent here. So there we have defined the Kelvin scale. Okay. So now Kelvin scale has been defined. So it start from the 0 Kelvin, and it may have a value up to infinity here. And the next point is that how we have defined the definition of Kelvin. So in the I don't remember the exact year in which the conference has been taken place. I think in 1954 itself the conference has been taken place, and there also they defined the definition of the 1 Kelvin. So they have taken a reference of triple point of the water to define the 1 Kelvin here too. Okay. Now, what is the meaning of triple point here? Triple point is a point at which all the three phases of the water, solid, liquid, and gas, coexist with each other. Coexist with each other here. Okay, just remember this one. Now, what are the properties at the triple point? So, there the triple point of the water is 0.61 kilopascal. The temperature is around 0.01 degrees Celsius here. Okay, and we know that 0 degrees Celsius 0 degrees Celsius, it is having a value of 273.15 degree Kelvin here. So I can say 0.01 degrees Celsius it is going to have a value of 273.16 degree Kelvin here. Okay. So from here you can see 1 Kelvin is defined as 1 by 273.16 part of the triple point here. Okay, That is how you have defined the definition of the 1 Kelvin here. So option number D is the correct one. Any doubt? So I have told you the entire history of the thermodynamic temperature scales here. So here there is one more term, thermodynamic temperature scale. Temperature scale is different. Thermodynamic temperature scale is different. Temperature scale simply means any scale which is used to measure the temperature. Thermodynamic temperature scale, thermodynamic temperature scale is something which is used to measure the temperature as well as it is independent of the material. Okay, and that thermodynamic temperature scale is nothing but it is a Kelvin scale here. That thermodynamic scale is nothing but it is a Kelvin scale. Okay, and how we have defined the Kelvin scale? The Kelvin scale has been developed on the basis of second law of thermodynamics. Okay, on the basis of second law of thermodynamics with the concept of heat engine, we have defined the thermodynamic temperature scale, that is Kelvin scale here. And the 1 Kelvin is defined on the basis of triple point of the water here. Any doubt? If you have any doubt, please let me know. Now, the next question. For which of the following situations, zeroth law of thermodynamics will not be valid? Now, what is the meaning of zeroth law? First of all, there are four laws of thermodynamics in thermodynamics here. The starting with the first one is the zeroth law of thermodynamics only. Okay, the first one is the zeroth law of thermodynamics only, which gives a concept of the thermal equilibrium here. So I don't think I have to define the zeroth law of thermodynamics here because that's a very simple case. When A is equal to B and B is equal to C, then A is going to be equivalent to C here. Okay, that is a simply a thermodynamic zeroth law of thermodynamics here. Now, zeroth law of thermodynamics form the basis of a temperature measurement. It create a basis of the temperature measurement. Why I'm saying that it is form a basis of temperature measurement? Because with the help of zeroth law only, the condition of thermal equilibrium has been defined. Okay, and in order to measure the temperature with the help of thermometer, the establishment of thermal equilibrium is very important for you. That is why it forms a basis of temperature measurement here. Okay, now just read the conditions under which scenario thermodynamics will not be valid here. 50 centimeter cube of water at 25 degrees Celsius is mixed with 150 centimeter cube of water at 25 degrees Celsius. So here you can see the temperatures are same. So I can say again the zeroth law of thermodynamics is going to be applicable here because the same substance are there, water is there, and there won't be any chemical reaction taking place here. Okay. In the next case, milk is given at 15 degrees Celsius. It is mixed with 100 centimeter cube of water at 15 degrees Celsius. Even though the temperatures are same, the substances are different, but there may be a chance the chemical reaction can take place. But in between the milk and water, there won't be any chemical reaction. So we can say the zeroth law of thermodynamics will be valid here. Okay. Coming back to the 5 kg of wet steam at 100 degrees Celsius is mixed with saturated steam. Okay. So here you can see uh, the system is at 100 degrees Celsius. It is a wet steam. Here we have a liquid plus vapor. Correspondingly, here we have a dry and saturated steam. So even though if you mix them, if you have a basic understanding of a simple TS diagram, temperature entropy diagram, here you can see I can show this. The wet steam I can show it here like point number 1, and the dry and saturated steam I can show it like here at point number 2. Even though if you mix it with each other, the final point is going to lie in between 1 and 2. So correspondingly the final temperature will remain same. That means at option at C we can also assume the zeroth law of thermodynamics is applicable here. Now at 20 degrees Celsius, water is mixed with 20 degrees Celsius of sulfuric acid. From the name itself, you can see there is a uh, oxidation is going to be taken place here. The chemical reaction will going to be taking place here, or energy is going to be released. Okay, so correspondingly, the temperature may increase or decrease depending upon the type of chemical reaction here. So zeroth law of thermodynamics is not going to be applicable in this case. Okay. Next part. Which thermometer is independent of the substance or the material used in its construction here? Okay, now just see. I have already told you the entire history of the temperature scales here. Okay, we have already seen the entire history of the temperature scales. Now just see what are the different type of thermometer which we covered in thermodynamics here. So here first we have a mercury thermometer. Okay, just see. First we have a resistance based thermometer here. Okay, then we have a thermocouple. Then we have a simple mercury in glass, mercury in glass thermometer. Then we have a ideal gas thermometer, which is of two type. The first one is the constant pressure thermometer, and then we have a constant volume thermometer. So there are total five thermometer which you should know here. Okay. Now in each of these thermometer, here we use one property to measure the temperature here. Okay, then that property which is generally used to calculate the value of temperature is known as the thermometric property here. What is the meaning of thermometric property? Thermometric property is that property with the help of which what we are doing, we are measuring the temperature. Okay. For example, in the case of resistance based thermometer, we are finding out the temperature by checking the change in resistance. If the resistance is changing, the temperature is going to be changed here. Okay. So just remember that part. In the case of resistance based thermometer, what is the thermometric property? Resistance is going to be a thermometric property. And I have told you here we have different temperature range. If you are measuring the temperature from minus 188 degrees Celsius to 0 degrees Celsius, the thermometer is going to be a resistance base in which you are using a platinum wire here, and correspondingly the resistance is going to vary in this way here. So in this way you can assume the variation. Okay, if the temperature range is lying from 0 degrees Celsius to around 650 degrees Celsius, there we assume the resistance is varying with the temperature of R equal to R naught 1 plus AT plus BT square. Even though in formulas are not important for you, just I am telling you because to visualize that how they are different to each other. Okay, now what is the value of R naught here? R naught is representing the resistance at 0 degrees Celsius, resistance of wire at 0 degrees Celsius here. Okay. Now coming back to the next thermometer, here we have thermocouple. Thermocouple is basically used. Thermocouple, uh, in this case, what we have, it works upon the Seebeck effect here. What does the Seebeck effect states? It simply states that if you connect two wires, two metallic wire of different materials like this one, and if you connect a voltmeter, let us say here we have a voltmeter. Now, if you maintain a temperature T1 at one end and temperature T2 at another end, so due to the temperature difference, an EMF is going to be induced in the voltmeter here. So higher the EMF produced, higher the temperature difference will be there. So just by measuring the EMF induced in the thermocouple, you can calculate the value of the temperature. And what is the temperature range here? The temperature range lies from 650 degrees Celsius to 1063 degrees Celsius here. Okay, from 650 to gold point, the thermocouple is generally used because high temperature is required to create a EMF resistance here, EMF voltage here. Okay, and the next thing is what is the thermometric property? The thermometric property is the EMF here. Okay, if you just see in the mercury in glass thermometer which we normally use in our homes or in our hospitals here, there the expansion of mercury is taking place due to the temperature rise. So there the length is going to be considered as a thermometric property. Okay, it may have any temperature range. Small temperature ranges are going to be there from I can say 0 degrees Celsius to 100 or 120 degrees Celsius here. Coming back to the ideal gas thermometer, there we have two type of thermometers: constant pressure, constant volume. Okay. In the case of constant pressure, volume is the thermometric property. In the case of constant volume, pressure is the thermometric property here. Okay. Just see. Here I have told you that before 1954, we have to define the temperature scale with the help of oxygen and gold point here. After 1954, what we have done, we have defined the thermodynamic temperature scale there. Okay. Now, when we have defined the thermodynamic temperature scale in the modern thermodynamics after 1954, there what we use, here we use an ideal gas thermometer to calibrate them. Okay, to find out the exact temperature values here. Just remember this one. Okay, so there we find the use of ideal gas thermometer here. And in the case of an ideal gas thermometer, it does not depend which reference fluid you are using, because there the ideal gas equation is going to be applicable. So the only condition is that the equation PV equal to MRT, it has to be followed here. That is an important condition. So it is independent of the material of the construction. So option number C will be the correct answer. Any doubt? If you have any doubt, please let me know. Next case, the gas constant R is equal to. Okay, so before proceeding with the gas constant here, let us understand what is ideal gas here. So in thermodynamics, generally we have two type of gases, ideal gas and the real gases. What is the meaning and what is the difference here? Ideal gas is a imaginary hypothetical gas, okay, which does not practically exist here. Uh, Generally, we study the ideal gas in thermodynamics because the analysis is very simple. If you say the case of real gases, the real gases behavior are very much different from the ideal gas. Now, what are the assumptions of the ideal gas? In that case, we assume there is no intermolecular force of attraction or repulsion here. Okay, no intermolecular force of attraction is there between the atoms and molecules. Second thing is that if you are compressing the ideal gas, the volume after the compression, it may reach up to zero value. That means the size of the atoms or molecules are so much small as compared to the size of the system that you can compress it to zero volume also. Okay, but if we see in the case of real gases, the intermolecular forces of attraction are going to be there. The force cohesion is going to be there, and along with that, the size of atoms and molecules are not negligible. They are going to occupy some volume also. Okay, just remember that part. Now, in order to study the ideal gas, we have ideal gas equation, which is also known as the perfect gas equation here. Now, ideal gas equation is written as PV is equal to MRT. What is P? P is the pressure. Okay, sorry, it is the absolute pressure here. Remember that one thing. Remember one thing here. There are two subjects, the thermal subject and the fluid mechanics. In the thermal subject, you are going to take the pressure as only in absolute form. Whenever you are doing any questions of the fluid mechanics or the hydraulics here, you always have to take the pressure in the gauge form here. That is very important for you. If any question is framed from the fluid mechanics, always convert the absolute pressure into gauge pressure. If the question is framed in the thermodynamics, always convert the gauge pressure into the absolute form here. Okay, that is very important thing. What is volume? Volume is representing the simply the volume here, that is meter cube, how much space it is being occupied here. M is representing the mass of the gas, it is in the unit of kg. R is representing the characteristic gas constant here. Characteristic gas constant, which is having a unit of joule per kg Kelvin. Okay, joule per kg Kelvin here. And T is representing the app temperature. Temperature is in the Kelvin scale here. Okay, you don't have to take the temperature in degrees Celsius. Now, in this case, we also rewrite the ideal gas equation in some other form, which is written as PV equal to nR bar T, where the P is same, V is same, temperature is same. What is N? N is representing the number of moles of a substance here. And what is a unit? Mole is the unit here. What is R bar? R bar is representing the universal gas constant here. Okay. Universal gas constant is having a constant value for all the cases, that is 8.314 joule per mole Kelvin here. That is the unit of the universal gas constant. Now, how the first of all, what is the meaning of number of moles here? See, like in our daily day-to-day life, we define the mass in the unit of kg. In the same way, in chemistry, the unit of the mass unit is going to the I can say the amount of the substance is represented in the form of mole. Okay. Let us suppose if I'm telling you that we have 1 mole of oxygen. What is the meaning of 1 mole of oxygen? 1 mole of oxygen is having the same amount of uh, oxygen which is equivalent to its molecular weight. So here you can see the molecular weight of oxygen O2 is 32. That means 1 mole of O2 is having a 132 gram of O2 here. Okay. And always remember that in 1 mole, how many number of molecules are there? How many number of atoms and molecules are there? There are Avogadro number of atoms or molecules here. Okay. Similarly, if you have 1 mole of CO2, now what is the molecular weight of CO2? It is 44. That means 1 mole of CO2 is consisting of 44 gram of CO2 here, which is again consisting of 606.022 into 10 to the power 33 atoms or the molecules here. Okay. Now, what is the relationship between the characteristic gas constant and the universal gas constant? You have to remember universal gas constant is having a constant value for all the gases here, but characteristic gas constant is having a different values here. So there we find that universal gas constant is equivalent to molecular weight multiplied by the universal characteristic gas constant here. Okay. So for example, the value of R for O2 is equal to R bar upon M, which is written as 8314 divided by 29, which will come out to be as 287 joule per kg Kelvin. Similarly, if you want to find out, oh sorry, it is not for O2 here, it is for air. If you want to find out for the oxygen, it is 8.38314 divided by 32 here. Okay. For the CO2, it is 8314 divided by 44 and so on. Okay, so that is how you uh, find out the values of the characteristic gas constant. Now here what we do, I am just specifying you the different formulas here. Just remember these formulas. We will cover those formulas in the subsequent lectures here. Okay. For air, you have to remember some values. For example, the first value is the CP. What is CP? Specific heat at constant pressure. What is the meaning of that? I will tell you later on. Okay. Because it is not a part of today's class here. So it is having a value of 1.005 kilojoule per kg Kelvin. Then we have CV, that is 0.718. Units are same. Then we have a R, which is CP minus CV. Okay, again characteristic gas constant, which is equivalent to 0.287. The same value, but it is written in the form of kilojoule per kg Kelvin. Then we have value of gamma, which is defined as the ratio of CP by CV, which is equivalent to 1.4 here. We can also write the formula of CP in form of gamma and R here. Okay. We can also write the formula of CV in the form of R and gamma here. So just remember these numerical values, because these values are not going to be there in the numericals. You have to use the values itself. Okay. So you should be aware of this. So that's it for this particular question. So here you can see gas constant R is nothing but it is a difference of the specific heat at the constant pressure and the specific heat at the constant volume here. Okay, that's a very simple case. Next, in a highly rarefied gas, the concept of this loses validity here. So actually, in the case of highly rarefied gas, the concept of continuum is basically loose here. Now, what is the meaning of continuum? Continuous, see, all the analysis which you are doing in your graduation in thermodynamics, in fluid mechanics, it is only possible because you are assuming the concept of continuum. Now, what is a continuum? Continuum simply means that the matter is present continuously at each and every point here. Due to the continuous presence of the matter at each and every point, we can simply perform the integration, or we can simply perform the mathematical calculations here. If the matter is not present everywhere, in that case you cannot use the mathematics. You cannot just convert any physical problem into the mathematical concepts, mathematical problems here, and you cannot perform the further calculations here. Okay, so always remember that the continuous simply means the presence of matter as a continuous here. So I can say the continuous presence of, or I can say, just give me a second, continuous presence of matter can be considered as a continuum here. Okay, so basically if you just see in this space, the planets are is not everywhere here. Okay, they are present at everywhere, but the gap between them, they are very large. Okay, so there we cannot say that the planets are present continuously here, so the concept of continuum does not get validated here. Okay, so there we can say the concept of continuum will be lost. Okay, the expression that is integration of 1 to 2 pdv gives the measure of work done during the, okay, steady flow, non-flow, reversible, open system, any system here. Okay, first of all, just see, then let us talk about the energy interaction first of all here. At the starting of the lecture, I have told you that in thermodynamics we have to study the energy interaction. Okay, the energy interaction can take place in two ways. When we talk about the energy interaction, I am talking about the transfer of energy through the boundary. Okay, so energy transfer through the boundary may take place in two ways. The first one is the heat interaction, the second one is the work interaction here. Now there is a proper sequence of studying the thermodynamics. Okay, how we study the thermodynamics? First we study the work interaction here. Okay, you are going to find out each and every formulas related to the work interaction. Then you will define the first law of thermodynamics here. And once you know the first law of thermodynamics, then you can simply you can derive all the formulas of the heat interaction here. Okay, so there is a proper sequence in which you have to proceed in the thermodynamics. Now the next thing is coming back to the work interaction here. First of all, just understand what is the meaning of process, what is the meaning of state, what is the meaning of quasi-static here, because these are some of the important terms which should be aware, which should be clear in your mind here. First of all, just see process, sorry, process nahi, we have seen the property. I have told you that property is representing the characteristics of the system here. Okay, that is the property. What is the meaning of state? State simply means condition of the system here. Condition of the system. What are the example of properties? Pressure, volume, temperature. All of these are the characteristics of the system. Now let us suppose you have a simple piston cylinder arrangement. Now the piston is at the position number 1. Okay, and in the piston cylinder arrangement there is some air or some fluid is there which is having a property of P1, volume V1, and temperature T1. So now you can see this P1, V1, T1 is nothing but it is representing the characteristics of the system here, which are the properties here. Now, once the system has attained a particular property, we say it has attained a defined state here. Okay, so due to this pressure P1, V1, T1, I can say the system has attained a particular state. What kind of state? So you can say, sir, when the piston is at number 1 position and the temperature is very high, let us suppose 100 degrees Celsius, pressure is very high, volume is very low, volume is very low. So I can say it is having a compressed state now. It is in the compressed state, or I can say it is having a hot state. Okay, so what is this hot is representing? Hot is representing the condition of the system, and how you are defining that it is a hot due to the pressure, volume, and temperature. So due to the characteristics of the system, you are defining the state of the system here. Okay. Now what happens here? Now, when the system has attained a particular characteristics, it has attained a defined state, we can say this is a equilibrium state here. Okay, the state one is the equilibrium state here. It is a equilibrium state. Okay. Now what is happening? Now let us suppose the piston is moving from 1 to 2. Piston has moved from 1 to 2. Now the system properties get changed. Now the properties are P2, V2 and T2. Due to the change in properties, what will happen? The condition will be changed. Now let us suppose as the piston has been moved from 1 to 2, the corresponding temperature has been reduced. So due to the reduction in the temperature, the corresponding state is going to be a cold state here. Okay. Now you can see a new state has been achieved due to the new properties. So always remember that whenever the properties are changing, whenever the characteristics are changing, the states are always get changed here. Okay. So this is a new equilibrium state. Now, what is the meaning of thermodynamics? So thermodynamics deals with the equilibrium states when the system has when the system is changing its state from one equilibrium state to the another equilibrium states here. Okay, we don't deal with the non-equilibriums here. We always deal with the equilibrium states here. Okay. Now you can see as the piston is moving from 1 to 2, in between, let us say the piston has reached the position A, then the piston has reached the new position B, then the piston has reached the new position C. So when the piston is moving from 1 to 2, new states are always coming up in during the motion here. Okay. So in between the equilibrium state 1 and 2, we have different type of states. State number A, state number B, state number C here. Okay. So you have to remember here we defined a process. What is process? Okay. First of all, just see what is path. What is path? If I simply create a pressure volume diagram, if I simply create a pressure volume diagram, so here you can see this is the state number 1 and here we have state number 2. Okay. At state number 1, we have a pressure P1, volume V1. At state number 2, volume is V2 and pressure is P2 here. Now, when the piston is moving from 1 to 2, it is carrying out a proper path here. It is carrying out a different states here in between the motion. So when I connect the different states here, here we define a path here. So this is our path. So what is the meaning of path? Path is representing the succession of the equilibrium states. Okay. So through which different states you have gone through the first equilibrium state to the final equilibrium state is representing the path. And when this path is properly defined, then it is known as the process. When the path is properly defined, then it is known as process here. Okay. Now the question arises, what do we want to find out here? Yeah. So here we have seen the definition of property. We have seen the meaning of state as well as the process as well as the path here. Okay. Now what is the meaning of quasi-static process? The quasi-static is a very important term in thermodynamics. What is the meaning of quasi-static process? Just understand in this way. Let us suppose you have a cylinder. Here we have a cylinder. Okay. And the slider is maintained at position number 1. Now you can see here we have some air. Here we have some air or some fluid is there at a which is having a property of P1, V1 and T1 here. Now if I just simply show it on a pressure volume curve, you are going to locate this with the point number 1 here. Okay. Now just see. Assume that I am putting a 1000 kg of weight. I am putting a 1000 kg of weight over this piston at once. Okay, I have just put entire 1000 of kg. entire 1000 kg of weight at once over this slider here, then what will happen? Suddenly the piston will move toward the bottom here at position number 2 in a very fast manner. Okay, at position number 2 it has attained P2 V2 T2. So now it can be located with point number 2 here. Okay, now tell me, do you know that what is the, okay, just see, first of all, the motion from 1 to 2 is taken place in a very fast manner. Okay, it is taken place as a very fast manner here. We don't know that what are the in between states here. We don't know what is the state, what are the properties of the gas when the piston or the slider is at A or when the slider is at B here. We don't know. Okay, now what is the meaning of quasi static? Now let us suppose, now let us suppose, okay, just tell me one thing, just think about it and just give me a response now. Initially, the slider is at 1. I have put 1000 kg of weight. The piston has reached position number 2. Okay. Now, the piston is at number 2 position here. Now, if I just remove the entire 1000 kg of weight from the piston at position number 2, the piston will again move back to 1 here. Okay. Okay, just give me a second. I am not able to explain it properly manner here. Just just I am trying to explain it one more time here. So at one position, you have put down the 1000 kg of weight, 1000 kg of weight, and the piston has reached the position number 2. Now let us suppose when the piston is moving from 1 to 2, at A position, the pressure was 100 kilopascal. I am assuming a random data. This is a random data. Okay. So when the piston is moving from 1 to 2 in a very fast manner, at A position, the pressure was 100 kilopascal. Let us say. Now tell me, now the new position of the piston is 2 position here. Now if I remove the piston, sorry, if I remove the weight at position number 2, what will happen? The slider will move again back to 1 here. Okay, passing through the A position. So whenever the piston is moving from 2 to 1, is it a necessary condition that at A position the pressure is again going to be 100 here? Tell me yes or no. Understand my question, what I am trying to say? When the piston is moving from 1 to 2, at that point of time, the pressure at A is 100 kilopascal. But now, as you remove the weight, and again the piston is moving from 2 to 1 here in the opposite direction, then it is necessary that at same position A, you are going to see the same pressure. Yes or no? Yes, give me a response now. Why? Why you are going to see the same pressure at A position here? Just understand, you have put 1000 kg of weight suddenly, okay, over the piston. The piston has moved from 1 to 2 in a very fast manner. And then you have removed the entire 1000 kg of weight suddenly. And then the piston again move back from 2 to 1 in a very fast manner. So it is necessary that at A position, the pressure will be same. It is not going to be it is not going to remain same here. Okay, because in this case, in between these states, in between the piston, in between the initial and final state, we don't know the states here. We cannot clearly define, because we don't know that how the atoms and the molecular movements are taking place. Okay, what is the randomness present between the atoms and molecules here? Whether the randomness is same or not, because you are not providing sufficient time to get to make the atoms or molecules stables here. Understood? Now understand what is the meaning of quasi-static process here. Now just see. Again, you are putting the 100 kg of weight over this slider. Now the question, now the way is different. First you have put the 0.001 gram, then you again put the 0.001 gram. So you are putting one by one small amount of weight over the slider. So as you are putting one by one small amount of weight, what will happen? The piston will go slowly from 1 to 2 here. Okay, so I can say when the piston is moving from 1 to 2, in between you are going to get different states. Here we have defined a state number A, then we have defined the state number B, and then we have defined state number C. So in between you are going to get a stable state here. The atoms and molecules are getting a sufficient amount of time to get stable. That means they are getting a sufficient amount of time to get in equilibrium with the surrounding here. Okay, so once the piston has reached position number 2, okay, so this entire process from 1 to 2 is going to be considered as a quasi-static process. Now what is the meaning of quasi-static process? Quasi-static process is a process which take place in an infinite period of time here. Okay, so I can say the infinite slowness is the characteristic of the this one here. Infinite slowness is the characteristics of the this quasi-static process here. Okay, or now you can see number one is a equilibrium state, number two is a equilibrium state. When the piston is moving from A, B, and C, all of these are the equilibrium state. So that simply means quasi-static process is a succession of the equilibrium states here. Okay, so as the piston is moving from 1 to 2, in between we are having a defined states here. Okay, so if I just connect these all of these points, the different states, we are having a quasi-static process here. Understood my question? So, understood my part here? So this is a quasi-static process. So now just assume the piston has, sorry, the slider has reached the position number 2, and over it we have a 1000 kg of weight. Now what you are doing? You are removing the weight one by one. In a small increment, you are removing the weight. So can I say that as the piston is moving from 2 to 1, in between states C, B, and A, you are going to have a same pressure, volume, and temperature, which is there when the piston is moving in the downward direction. Okay, so when you are removing the weight, you are going to see the piston is moving in such a way the property will remain same from 2 to 1. The in between properties and the states are going to be remain same. Okay, so there we define a definition of reversible process. So what is the meaning of reversible process? Reversible process is a process in which you are moving from initial and final state, from initial to final state, and at the conclusion of the final state, okay, what you are doing? You are moving again backward in a reverse manner, and in between you are getting the same properties which you have attained in the initial movement here. Understood? That is a definition of reversible process. Or you can say reversible process is a one which can be uh, I can say reversible process is a one which is carried out in such a way, if you reverse this process, you are going to have a same equilibrium states which is there in the forward process. Okay, so that is a reversible process. Now just see, there is a one parameter. As the piston is moving from 1 to 2 in the downward direction, there is a friction also. Okay, there may be a chance we have a friction also, and due to the friction, the the energy is going to be loose in the form of heat. So always remember that quasi-static process with friction is going to be considered as an irreversible process. What is the meaning of irreversible process? Irreversible process is a one in which the same properties are not going to be attained during the forward process and the reverse process. Okay, the quasi-static process without friction is going to be considered as a reversible process. What is the meaning of reversible process? Reversible process is a one in which you are going to have a same properties or a same equilibrium state during the forward process and during the reverse process. Okay, and in thermodynamics, Generally, we don't consider the friction into our analysis here. So that is why we say that quasi-static process is a reversible process. Okay. Practical example, there is no practical example of quasi-static process because infinite slowness is the required characteristics here. Okay, and there is no such process which carried out in an infinite period of time here. Okay, any doubt? So this is a basic definition of reversible process here. Quasi-static process as well as the property state etc. Now, uh, the expression PdV gives the measure of work done. Now, what is the meaning of work done here? So now just see. In thermodynamics, the energy interaction take place due to the two reasons, either due to the work interaction and due to the heat here. Both are considered as the energy in transit. Energy in transit simply means the energy which is flowing through the boundary. Okay. Now in mechanics, how do we define the work? If you are applying the force and it is displacing a body through a distance, through some distance in the same direction, we say it is a the work has been performed. The work has been calculated with the formula of force into distance. Okay, but in thermodynamics, the definition of work is little bit different. Okay, thermodynamically, we say that work is said to be done by a system if in imaginary condition, or I can say if uh, we can utilize the system to raise the external weight. Okay, either we can raise the external weight or either we can lower the weight here. Okay, so we can say the system is capable of doing work. What is the meaning of that? For example, if you have a wire, okay, and through this wire the current is flowing, through this wire the current is flowing. Now if I ask you that whether this flow of current can be considered as a work or not, you can simply say it is not. Why? Because there is no displacement taking place. But in thermodynamic sense, the flow of current through a wire can be considered as a work here. Why? Because you can connect a simple motor here or a pulley here, and by running the motor or a pulley, what you can do, you can lower the weight or you can raise the weight. Okay, so we can say the flow of current can be can be utilized to perform some work here, can be utilized to displace the weight by some distance here, so it is capable of doing the work here. Okay, now the next part, what is the expression here? Now let us suppose here we have a piston and initially the piston is at a position of A. Okay, at this point of time, thus inside the piston cylinder arrangement there is some air which is maintained at a pressure of P, and the area of the piston is capital A. Now what is happening? I am assuming the pressure which is acted upon the piston, it is displacing the piston by a very small or a very infinitesimally small distance here. It is a moving a piston from A to B. Okay, this distance A to B is very small. Okay, so you have displaced the system by, let us say, dx distance. Okay, so or I can say this movement from A to B is very small. It is performed quasi-statically here. So in that case, if you want to find out that what is the work done here, so you can simply say the work done is going to be force into distance. That is the work done here. Now from where the force has been acted, it is due to the pressure here. So I can write the pressure into area will be the force into the distance here. Now what is the meaning of A into dx? ADX is representing the volume by which the piston has displaced, the volume by which the air or fluid has been displaced here. Okay, so ADX is representing the displaced volume. So I can write the work done formula will be pressure into change in volume. Okay, now see what I have taken. I have taken an assumption that from A to B the piston has moved very slowly. Okay, and the distance has been covered a very small here. Okay, so now let us say if the piston is moving from initial position A to final position, let us say B here. quasi-statically or in a very slower manner here. So we can simply say the work done is going to be equivalent to integration from 1 to 2 of PdV here. Okay, so that is a formula. Now, this formula is defined under for what conditions here? This has been defined for the closed system first of all. Why? Because the mass is constant inside the piston cylinder arrangement. Here we have assumed the process has been carried out quasi-statically here. Okay, so quasi-static simply means it is a reversible process. Okay, now in the thermodynamics we say that closed system is a non-flow process here because the mass is not flowing, and the open system is considered as a flow system here where the mass is continuously flowing. So I can say the option number B will be the correct answer. Next part, the vapor pressure of the solid ammonia is given by this expression and that of liquid ammonia is given by this expression. What will be the triple point temperature of ammonia here? So let's understand here. First of all, every substance is having its own triple point here. The triple point is a point where the solid, liquid and vapor are coexist with each other. And it is a point where the degree of freedom will become equal to zero. Why? Because the degree of freedom is representing the number of parameters which are required to fix the state here. So basically the triple point is a fixed point. You cannot change any parameters here. So that is why the degree of freedom is going to be zero. Okay, it is a fixed point here. Now if you just see, the solid ammonia and the liquid ammonia both are defined in terms of pressure and the expressions are different here. Can I say that at the triple point both of these ammonia are going to have a same pressure, both of these ammonia are going to have a same temperature here? So correspondingly I can write 23.05 minus 3754 by temperature, it is going to be equivalent to 19.49 minus 3063 upon temperature here. And if you equate this, you can simply find out the value of the final temperature here. Okay, so that's a very simple case. You don't have to do the entire calculations here, just solve it and get your final answer. Okay, and the final answer of this question, I don't have the exact answer here just right now. So maybe I think the answer will come out to be around 195, 195.2. Okay, just do the calculation and find your answers here. So that is our today's topic here. Now tell me if you have any doubt. I will share the theoretical notes of the first chapter with you. Okay, along with this PDF. Go through the theoretical notes, then go through the questions here. Okay, in that case, in this way, you are going to cover up the theoretical questions as well as the numerical questions also, practice questions also. Along with that, also start doing the previous year questions of ESC, GATE, as well as all the SSC JEE exams here. Now tell me if you have any doubt. So that is for today's class here, and the remaining things we are going to see in tomorrow's class. Okay. So I'm closing this session, and if you find any doubt or in any question or in any topic here, you can simply message me on WhatsApp either personally or you can tag me in group also. Okay. You don't have to do the lots of questions here. Okay. Just see, just try to solve at least 50 questions from each and every topic. That is a simple fundamental. Just try to solve 50 questions from each and every topic and just see the the theoretical notes which I'm going to share with you. Okay. Just try to solve the question related to that things. 30 questions related to that topic which I am going to share with you in the theory part, and the remaining top 20 questions should be from that particular things which is not covered in the theoretical topics, because entire thermodynamics is not, I'm not able to cover the entire thermodynamics in few months or in few days here. So you have to go through those questions also which is not a part of your syllabus. Okay, and if you just solve the ESC question, there you will find that what are the different type of thermometer, what are the different type of temperature ranges here, external values you are going to see there. So all of those type of questions you also have to prepare. Okay. So just try to solve 50 questions from each and every topic. Out of these 50 questions, 30 questions should be one, which is, I can say, which is relating to the theoretical notes, which I'm going to share with you. And the remaining 20 questions should be one, which is not covered in the theoretical part here. Okay.